So in terms of free space, so free space, they're not being used, but it still takes up your physical memory. And we want to be able to use this efficiently. Now, when the address space does not fit into the physical memory, that's a problem. So a simple idea was to use segmentation, where it's just a contiguous portion of the address space of a particular length, meaning logically different segments. So for code, stack, and heap, you're going to have base and bounds for each. Okay, so instead of one big memory, we're talking segments, code, stack and heap. And for each portion, we're going to have base and bounds. That's really it. So each segment will be placed in different part of physical memory. So base and bounds exist per each segment. It's a little bit more finer grain. So here, right. So you're going to now have to have segment name, but also different base. Right. So here we have code starting at 32K. So we list that. The size is 2K. Heap starts at 34. Current size is 2K. Stack, on the other hand, starts at 28. We're going to talk a little bit more a little later, but stack goes in a different direction. Right. So size is 2K, but it actually goes in the other direction. So now, address translations and segmentation. Now, with segmentation, translation is just a little tiny bit more complicated. And first, we're going to look into the code part. So the physical address is basically base plus the offset. So here, let's say we have a program code here, and the offset of the virtual address 100 is 100, right? Because it starts from 0. Now, here the code starts at 32K. The base starts at 32K, right? So the if your virtual address is 100, the physical address is simply 32K plus 100, which would be 32,868. Simple enough, but heap is a little bit different. So here, the virtual address plus base is not the correct physical address. Instead, it's the offset of the virtual address plus base. So what we mean by here is that, first of all, heap base starts at 34K. Okay. Now, at the heap here, segment starts at virtual address 4K, which is 4096. And now the virtual address is 4200. So what we need here is that you're not actually going to add the virtual address, but you need to look at the offset here. Right? So the virtual address 4200 minus 4K, which is 4096. So your offset is 104. Right? So your heap starts at 34K, so you add your offset, 104 plus 34K, and that's the desired physical address. So basically, you look at the portion, your segment, and where does your segment start? Right? Your virtual address of your segment starts at 4096. So 4200 means you're actually 104th within your segment. Got it? Now let's talk about segfault. So this is an illegal address, let's say, such as I'm trying to access 7K, which is not in use. So this is beyond the end of the heap. Then OS exception is raised and segmentation fault. Now, since we have segmentation, now we have different segments. So we need to know which segment we need to go to. Right, so we have three cases, right? Code, heap, and stack. So we need 2 bits. Right, so 0, 0 means code, 0, 1 means heap, stack means 1, 0. So we will use the top 2 bits to indicate which segment, and the rest of the bits for the virtual address. So example, virtual address 4200, like in the heap, in the previous example. So heap was 0, 1, so you put 0, 1, right? And this was, what was it? What was it, 104? Yeah. So this is 104, right? Heap segment, offset 104. So if you want to put down code for segment selection, this is how it looks like. So first, to get the segment, you're going to do a virtual address and segmentation mask. Now, mask here will be 1, 1, the rest of the 0, because we're using 2 bits to know which segments, right? So you want to do an AND, just for 2 bits. So you put 1, 1, so that's segmentation mask. Then you shift, right? 12, because we have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These bits, the actual address, we have 12-bit space, right? So you do from your virtual address, you do a AND with the first 2 bits, and then the rest of the bits you shift. So you have that segment. Now then, the offset is virtual address and offset mask. Offset mask as contrast to seg mask, all the rest of the 12 bits is 1. Then you will get the offsets. And then you do an if clause. If offset is larger than your bound of the segment, it means you're trying to access beyond your space, then you raise exception. Otherwise, your physical address is base of the segment plus offset. Right, and you put that value in the register. All right. By the way, do all of you guys have access to the textbook? You have it? It's free, right? So at the end of the textbook, there's a homework. I'm not telling you to turn it into homework, but it's like an exercise. So what's good about this book is the homework at the end of each chapter is actually writing code or running code. So he has a link, a GitHub link with all the codes of the homework where you can actually download and run it to actually experience all the concepts that you learn. So I strongly recommend you do it. You don't need to submit. I trust you guys. You guys are big boys and big girls. Make this good decisions. Go practice. Trust me, that's going to help you. Okay, you don't have to do all of it, but some of them, especially the ones if it's unclear, you don't even have to type. The code is all there. So try out. Yeah, so notice that we talked about the code segment. Suvin, could you turn on the AC, please? Yeah. We talked about the heap and code, but we didn't talk about stack, right? So the conceptually not very different, but the key difference here, as I mentioned, is the direction, right? Stack moves in the opposite direction. So in the table here now, we need another column. Say, does it grow positive or negative? Right? Code and heap, they grow positive, while stack grows negative. So you're going to need another bit. So that's extra hardware support. Now then, people thought, systems people are always about efficiency. So how can we be even more efficient? Right? So we have these different segments. So now we're not tied into one big chunk where it's inefficient. So we did achieve better efficiency, but can we do better? And the one idea is, how about we actually share, right? Segment can be shared between address space. And interestingly, this code sharing is, still in use by modern systems. And you now also need extra hardware support for that. So what we do here is, basically you add protection. Okay, if you want to go read, that's fine. You can go even write, or you can just read and execute. So it's almost like our, file mode, right? So basically protection bits. So a few more bits per segment to indicate permissions of read, write, and execute. So you can share, but importantly, you also add protection, right? You don't want other parts of the segment and go change something that shouldn't, right? So you could just say you can only read. Right? So you share code, better efficiency, while still have that protection. So compared to just one big memory space, obviously with segmentation, this is, finer grained, but some people argue, let's go even further, right? Because we could even argue what we just did with 3 segments is coarse grain. But in the old systems, there were even systems that even had even finer grain segmentation that could allow more flexibility for the address space. But then you're going to have to support many segments, more hardware support with a segment table. Right? So one might feel enough is enough. So I think most systems today just go with a coarse grain. Now, in terms of OS support for fragmentation, so as you allocate space and all that, there's going to be a bunch of tiny holes of free space, right? So it's just going to happen. So like, for example, here, like, oh, there's 8K and there's whatever, 2K, whatever, right? It's not contiguous. They're all spread out. So there could be cases where, I need to allocate, 24K, but I need it to be contiguous. But let's say the free space is more than 24, but none of them contiguous, large enough to actually satisfy 20K, right? So here, 8K, maybe 2K, this is what, 14, whatever. So in total, you have 24K free, but if somebody requests 20K, you can't actually satisfy the request. So that sucks. So the way to solve this problem is compaction. So rearranging the existing segments in physical memory. Something like this. All right? So it looks pretty, but for system perspective, this is very expensive. Because first of all, you're going to have to stop running that process. You're going to have to copy that somewhere. You're going to have to change segment register values and all that, which is a little too much, to be honest. All right. So the bottom line is there's no perfect solution. Right. So you have to live with it. There is a fix, but it's not a perfect fix. Yeah, that's it. It's a short lecture. Any question? Yes. So that's unused. Yeah, in this case, yeah. Because we had 3, right? So 1 bit would be only 2. But we have 3 cases. We have 1 bit, not enough. So you have 2 bits. So there has been some proposals to say, hey, we don't want to waste this 1 bit. So they like add code and heap together and then try to differentiate within. There's also like implicit way of doing it, saying instead of specifying explicitly, which is what we did, implicit would be if you just look at the instruction, you kind of guess where it is. Because stack is usually like local variables, right? Heap are the memory that you get. So sometimes based on the instructions, you look at the command and then you kind of guess where it is. So there are different ways of doing it. But yeah. Good question. Yes, sir.
What happens when
Stack and heap meet each other? Meeting's fine. You don't want to exceed, right?
I mean, what like after they meet each other?
You run out of you run out of memory, right? You run out of memory.
What if there is still not?
Then you have to adjust, right? Maybe you have to change. So you're saying the code. I mean, like you're saying what? So always they meet, but you have some space. I mean, there could be ways to actually move, but it's costly, but it's doable. Yeah. I mean, that depends on the OS designer. Mm-hmm. Page 45. So basically we want, so basically this part tells you which segment, right? But the virtual address was what, 14 bits? But we only want the first 2 bits. So we're just basically shifting them right so that we know just a segment. Oh, because yeah. You get, but what we're saying is, however, let's say it's 111. It's unused 10, but you still have all zeros in the back. But you don't need that because you just want value 3 or 2, whatever it was, because you're using here bounds of code, bounds of stack or heap. If you don't do shift right, this is a very large number, right? Instead of 0, 1, or 2. You know?
I think the question was, why can't we just shift down fast?
So if you shift, yeah, good question. This looks cool, yeah. It looks like a code written by some. I mean, but this is good readability in a way. You know what I mean? Because I think your way, perfect. But let's say if we put here just that, is it intuitive enough to know what that line of code is doing? So this is sort of like documentation without documentation. That makes sense? Yeah, good question. Right. A quick reminder, we have a lecture on Wednesday. Okay. All right. Thank you.